Hi, in the second part of this lecture, which introduces cardiovascular physiology, we're going to explore the effects of pressure on how pressure forces fluid to go through tubes. So we're going to be looking at some physics properties in order to explore this concept. The application is going to be the flow of blood through blood vessels. So let's start with this idea of pressure. If you've ever inflated an air mattress before, or like an inflatable beach ball, the air that you push in is under a lot more pressure than the surrounding area. And you know this because if you poke a hole in that beach ball or that air mattress, air is going to flow out of the beach ball or air mattress to the surrounding area because the pressure in the beach ball or the air mattress is greater than the pressure in the surrounding area. So there's a generally accepted concept that pressure gradients cause flow. Now this is true for both fluid and air. So again, from a weather perspective, if you have a high pressure system and a low pressure system, that causes wind to go from the high pressure to the low pressure system. For fluid, if you have a high pressure system and a low pressure system, the fluid is under a lot of pressure, it's going to push the fluid down to the low pressure system. So fluid flows down its pressure gradient. So let's write that down. So what that means is that if I want to get blood to go in this direction, I need a higher pressure here than I do here. So what generates the pressure in the cardiovascular system? It is mostly the heart. So the heart, by contracting and relaxing, generates the pressure that is needed to move blood through the blood vessels. Okay, so how do we measure pressure? Well, there's a bunch of different ways to measure pressure. When we measure air pressure, it can be measured in terms of atmospheres, kilopascals, but in the cardiovascular system, they have relied on an old school way of measuring it called millimeters of mercury. So the typical and common way to assess or measure pressure is called millimeters of mercury. And Hg is the chemical symbol for mercury. Now, this is an old school way to measure pressure. You might remember way back when that thermometers used to be made of mercury. Mercury is a metal that is very pliable, it's very malleable, and it changes its density under temperature and pressure changes. So the reason why mercury was used in a thermometer was because if you had the right length tube and you cooled off the mercury would shrink. When you heat up the mercury would expand. Now, pressure is kind of measured in that same way. When you apply a lot of pressure to the mercury expands. When you take the pressure away, the pressure shrinks, and they would have the scale and measure how many millimeters up did that mercury go. We don't use mercury anymore because it is a neurotoxin. However, the terminology stuck. So in human physiology, pressure is measured in millimeters of mercury. That's not going to mean anything to you because you have no mercury scale to look at. But you would know that a greater number means a higher pressure. So if I told you that something is 100 millimeters of mercury versus something being 50 millimeters of mercury, you should know that 100 is greater than 50. And since what we're really looking at is not absolute pressures, but what are called pressure gradients, all we're really looking at is which number is higher. Okay, so now that we've introduced that, let's take a look at a tube. So this is a tube, and what it's doing is describing this idea of fluid potentially going through the tube. Now notice that the fluid is going in a particular way. It's going this way. Now in order to get fluid to go that way, you would need a higher pressure at this point than you would down this point. And that, again, is because fluid only moves down its pressure gradient. So in order to get fluid to move, P1 has to be greater than P2. Now, that looks a little bit mathematical here, but really all of this is saying is that I have a pressure at this point, and I'm calling that P1, and I have another pressure at this point, and I'm calling that P2. Now, this is a mathematical term. It's called change in pressure. That triangle just means change or difference. So change in P is the same thing as a pressure gradient, meaning there is a difference in pressures. Now, in this case, P1 needs to be greater than P2 in order to have the difference. So let's take a look at some examples. In this example, P1 is going to be 100 millimeters of mercury. P2 is 100 millimeters of mercury. There is no pressure gradient. So even though there's a lot of pressure, 100 millimeters of mercury is a fair amount of pressure. So even though there's a lot of pressure, because the numbers are equal on each side, no one side is pushing harder than the other, so fluid just stays there stuck under a lot of pressure. There is no directional flow of fluid. However, let's take a look at this example. In this example, we have a case where we have 175, and we have a case where we have 415. The flow, or the movement of fluid through those tubes, is equal. And that is because the gradients are equal. So let's look at this top example here. In this top example, the change in pressure is 100 minus 75. That is 25. Down here, the change in pressure is 40 minus 15. That is 25. So because the pressure gradients are equal, the flow of fluid is going to be equal. So this is a good time to talk a little bit about fluid flow. Okay, so I said fluid flows down its pressure gradient, but we're actually going to define flow. Flow is defined by the amount of fluid that passes a certain point per unit of time. Since fluid is usually measured by volume, not weight or some other amount, we can change this to volume. Of course, there's a lot of different ways to measure the volume of something, but in science, the typical way is milliliters or liters, whereas perhaps in a layman's world, you would use gallons or quarts or something like that. So for instance, if I were going to go to like a big box hardware store, I might buy a 5-gallon bucket. And let's say that I turn on my faucet. Now my faucet is a tube. And I'm going to collect water in this 5-gallon bucket. If I collect all 5 gallons in 1 minute, then my flow is going to be 5 gallons per minute. That's how much I've collected. But if I turn the pressure down on my faucet, maybe I only get 2 gallons per minute. So that's an example that might resonate with your day-to-day life. In human physiology, we're interested in the volume of blood that is going through blood vessels per unit of time. So that is flow. Now I also want to say that flow and something called flow rate are used interchangeably. So we can go ahead and throw in this other term, flow and flow rate. Now, flow and flow rate are a product of the pressure gradient. The greater the pressure gradient, the greater the flow rate. Okay, so I'm going to give you an example of this. And probably the best example is a garden hose, but you could use a generic kitchen faucet too, and it would pretty much describe the same thing. So you're going to turn on your faucet. Let's just say it's the outside faucet with a garden hose connected, because that makes a nice little tube. If I don't turn it on very much, I don't have a lot of pressure. Now out here is a certain pressure. It's pretty low. It's not a high pressure. So we're going to turn on the faucet so that there is a pressure gradient. The pressure in the faucet is greater than the pressure in the air. Consequently, fluid is going to flow out of the faucet and into the bucket that I'm now collecting. How much fluid? Well, it depends on the pressure gradient. If I want to collect more fluid, then I need to increase my pressure gradient. Remember, out here is constant. This is a constant pressure, this air. So I would need to increase the pressure in my faucet to increase the gradient. Now, if you've ever had an exploded pipe before that's under a lot of pressure and fluid is going everywhere, whatever fluid that might be, you might be tempted to, take your t-shirt and wrap up the pipe, hold your hands around it. You're trying to counteract that pressure. If you apply your own pressure successfully, then the amount of pressure under the pipes minus the amount of pressure you're applying decreases, and therefore the amount of fluid that is lost also decreases. So there's an example of how fluid flow is directly proportional to pressure gradient. Now, mathematically, we can actually kind of expand on this. So what we have is flow, or flow rate, however you want to say that, is proportional to what is called the pressure gradient, we've already defined that, over something called resistance. So pressure gradient, again, is going to be the difference in pressure between starting and ending point. Resistance is going to counteract that. So anything that adds resistance to a system is going to reduce the flow. So what could affect the resistance? There are really three major things that are going to impact resistance. Okay, so one thing that would increase the resistance is actually decreasing the diameter of the tube. So if you have a big tube, so big diameter, big tube, then fluid moves pretty easily through that. But when you start taking that big tube and you start shrinking it down, the fluid is going to encounter a lot of resistance. You already know this to be true because you have worked with straws. So if I were to give you a coffee straw, which are like those tiny, super thin straws, and then ask you to go suck a milkshake out of that, you'd be like, yeah, I can't. Why? Because there's too much resistance in that tiny, narrow tube. But if I give you a Slurpee straw, you might actually do it, right? So therefore, you can see that Slurpee straws are going to be bigger. It's easier to suck through because there's less resistance, so there's more flow of fluid from the cup to your mouth. So diameter of a blood vessel is actually the #1 driver of resistance in the cardiovascular system. The smaller the diameter, the more resistance you're going to encounter, which is going to reduce the flow through that vessel. Okay, a second thing that will impact resistance is length of the tube. So tubes can come in various lengths. And again, I'm going to direct you to the straw example, and I actually do encourage you to try this if you happen to have plastic straws, which is kind of a no-no at this point, but if you happen to have them, go ahead and try this. Take a straw and cut it so it's super short, and then try sucking water through it, and what you'll find is it's super easy. And then take the long straw and suck water through it, and what you're going to find is you have to apply more force to suck water through the longer straw because the length of the tube is going to impact resistance. The longer the tube, the more friction that fluid encounters, and therefore the more resistance there is. So longer tubes are going to have decreased flow rates compared to shorter tubes. Now the third one is viscosity of the fluid. Now in our body, the fluid is blood. But again, with your own experiences, think about taking a straw and sucking up a Slurpee or a milkshake, which has a much higher viscosity over something like water. And you know that sucking something with a high viscosity is going to be a lot more difficult than sucking water. So the greater the viscosity, the more resistance and the lower the flow. So now that we turn and take a look at the cardiovascular system, I'm going to tell you that we need to be able to move a certain amount of blood per unit of time. And typically the amount is like 4, and in adults, probably about like 4 liters of blood need to go through our body per minute. That's what's called cardiac output, and that's a pretty typical amount at rest. Now, when you exercise, it needs to be greater than that, but at rest, 4 to 5 liters per minute is about right. So that's your flow rate. Now, how do you get it? You get it by changing the pressure gradient over the resistance. So by increasing the pressure gradient, you get a higher flow rate. Well, what generates the pressure gradient? Well, that's going to be the heart. So when the heart works harder, that's going to generate more pressure and give you more flow rate. The resistance, however, is going to pose a problem to easy flow. So in our cardiovascular system, the diameter of the tubes can change. This is mostly true with the artery and the veins to a lesser extent. Now remember, the arteries and the veins are going to have smooth muscle around them. And as you learned in a previous lecture, if you constrict that smooth muscle, you constrict or reduce the diameter of the tube, which is going to increase the resistance and therefore decrease the flow rate through that tube. So smooth muscle around the arteries is constricted, is going to decrease flow rate by adding more resistance. Now, what can you do about that if you have constricted arteries all the way around? You can increase your pressure gradient. How do you get that? Your heart has to work harder. So having chronically high blood pressure is not usually a good thing. And high blood pressure can be reflective of what are called vasoconstricted arteries. Now the tube length also applies, but the tube length in our case is fixed. In other words, we're not changing our tube length in a dynamic way. So we kind of ignore that one. The viscosity one is interesting. In general, we ignore that principle as well. However, there are cases where we probably shouldn't. Your blood viscosity, or how thick and chunky your blood is somewhat a property of how many red blood cells there are. So when there's lots and lots of red blood cells and not a lot of plasma, your blood becomes pretty viscous and therefore adds to the resistance. Now your body has natural ways of kind of making sure that you don't get, dangerously high viscosity levels, but there are situations where endurance athletes have in fact injected hormones that increase their red blood cell counts beyond what they should ever be. And in doing so, make their blood more viscous. So what does that do? That increases the resistance. What does that do? That means that you have to create a greater pressure gradient to counteract that resistance. In other words, if you're moving maple syrup through your blood vessels, your heart is going to have to work a lot harder to do that. That ends up causing hypertrophy of the heart, and for reasons that we'll get into in a subsequent lecture, that can lead to something called congestive heart failure, which is fatal. So now that we've covered that, I want to show you a couple more pictures. This one right here is talking about the flow with the radius, or the diameter in this case, of the tube. So it's showing the same beaker. You have 2 glass tubes coming out of that beaker. One has a much larger diameter than the other. So you'll notice that in this case, much more fluid goes out of the larger diameter tube than the smaller diameter tube. So by shrinking the diameter of the tube, you increase the resistance to decrease the flow rate. I would like you guys to apply your what you just learned to this problem. Take a look at these tubes, assume that the fluid that goes through them is equal and that the pressure gradients are equal. Which tube is going to have the most resistance and which tube has the least resistance? Go ahead and pause the video and see if you can answer. Okay, so we know that the driver of resistance is going to be tube diameter. So the first thing that we want to look for a high resistance is a small tube. And not small necessarily short, but small diameter. We have 2 candidates here. We have this one, and we have this one. So now that we've identified the tube that has the smallest diameter, now we're going to look for something else that might impact resistance, in this case length of tube. The longer the tube, the greater the resistance. So the tube that has the most resistance is going to be this one. Likewise, the tube that has the least resistance is going to be this one. Biggest diameter, and it's the shortest. Okay, we have one more thing to talk about and we're done, and that is flow velocity, which is not the same thing as flow rate. So flow velocity measures the speed of the fluid through a point. So people tend to think that flow velocity and flow rate are essentially the same thing. But I'm going to take you back to that garden hose example and explain why it's not. So I have a garden hose. I'm going to turn on the faucet to full pressure, and then I'm going to have a bucket, and I'm going to measure how much water I collect in my bucket in a minute. Let's say I get 5 gallons a minute. Okay, now what I'm going to do is keep the pressure gradient the same, but I'm going to put my thumb over the tip of the faucet. How many people have done that? And what happens to the water? When you put your thumb over it but leave just a little crack, now suddenly all the water is forced through that tiny little opening and comes shooting out really fast. Now, if I were to spray that fluid down into my bucket, guess what? I would still only be getting 5 gallons per minute. But because I put my thumb over it, I've increased the speed at which the fluid exits. So I haven't changed my flow rate, but I've certainly changed the velocity. Anybody who's ever tried to wash a car with a garden hose and no attachment knows this is true. Use a regular garden hose and the fluid's just like not enough pressure or speed to wash off the dirt. Put your thumb over it and suddenly that fluid comes squirting out. Again, same amount of fluid per unit of time, but the velocity went way up. So flow velocity is going to become important when we talk about atherosclerosis, but the example of the garden hose illustrates something that is important, which is that if you are forcing fluid through a tube and you suddenly constrict the tube to a really narrow point, the fluid is going to speed up to get past that point. So flow velocity increases when you decrease diameter within a little spot. Okay, so just very, very briefly, if I have a tube and it's got a certain diameter to it, and then I go ahead and, so here's my wall, and now what I'm going to do is I'm going to create a pinch point. So this would be like, oh, I don't know, artery plaque maybe. So fluid is coming through, blood is coming through. Now it has to go through this narrow pinch point here. And what happens is the fluid is now going to speed up to try to get through that really fast, like so. So we'll see this again with atherosclerosis in another lecture. All right, that concludes our introduction to cardiovascular physiology.